All right, starting chapter 5 today. And in chapter 5, we're going to be working on areas and volumes. We're going to start with areas. Now, we've found areas before. And in order to find an area, we just took the integral of the function. We found the area between a function and the x-axis. So if we have a function that looks like this, when we found the integral from a to b, that was this area right here. But what if we've got two functions? What if we've got function f of x and function g of x? What is the area between them from a to b? Well, in order to find that area, what we're going to do is we're going to take the integral of the big function minus the little function. So in our example that we've got over here, the big function is located above the little function. So f of x is the big function, and g of x would be the little function. So let's take a look at this one. We've got the function y equals e to the x. We know what y equals e to the x looks like. Goes through 1, keeps climbing. And we know what y equals x looks like. Now, we would like to find the area that's bounded by those two between x is 0 right here, and x is 1 right here. So this is what that region would look like. So if we're looking for that area again is going to be the integral. Now, where do our x's start and where do our x's end? Well, our x's start at 0, they end at 1. And then I've got to take the big function, which is the e to the x, minus the smaller of the two functions, and the red function y equals x is below e to the x, so that's considered the smaller function. We can put this into our calculator. If we do so correctly, why don't you check it out? Press pause, come back with your answer, and compare it to mine. My answer, I believe, was 1.218. So that's areas between functions. Now here we're going to be asked for the area of the region enclosed by this parabola and this guy. Well, from where to where? And they don't say. They just say the area of the region enclosed, and so these must intersect and trap a certain area inside of them. So let's take a look at y equals x squared. And let's take a look at y equals 2x minus x squared. Now let's see. If x is 0, y is 0. If x is 1, I'll put a 1 in here. I believe I'm going to get 1. And when x is 2, I believe y is 0 again. So I think what I've got here is I've got a down opening parabola for sure, because it's minus x squared. It's going to go something like that. But we can see that region that is enclosed. So they don't always have to give us where the region starts or where the region ends. Sometimes it's up to us to figure it out. Sometimes it helps too to label these guys. This is y equals x squared. This is the y equals 2x minus x squared. In the region that we're talking about, it is this red function, which is the larger, because it's up above the blue function. So if I'm looking for the area, I'm going to take the integral. And this started when x was 0. We found they intersected again when x was 1. So the x's start at 0 and the end at 1. And then we have to take big function, which is this 2x minus x squared minus the little function dx. This is one we could do with a calculator, without a calculator. I think either way would be fine. Now, as long as we do large function minus smaller function, we will always end up, no matter where this region is, we will always end up with a positive answer. So you might want to check this one out. You do this on your calculator. I think we get this. Others might express this as 1/3, but I believe that's the area of that region. All right, example 3, they don't ask us to actually find any particular area. It asks us, though, if we've got some velocity curves for two cars, car A and car B, what does the area between the curves represent? Well, the area under a velocity graph gives us displacement. Remember, this is a velocity time graph. So the area, and let's say we cut this off at 5. What's the area between these guys? Well, it's going to tell us the displacement. It's going to tell us how much greater A's displacement is compared to B. And I should be really specific about this. I should mention from t equals 0 to t equals 5. Now, to t equals 5, sorry about that. Okay, now they didn't give me any units, so I'll just call it a t of 5. Would it have been okay to say this? How far A is ahead of B? At t equals 5. Would that have been okay to say? A's got a bigger displacement. A has definitely traveled further. These displacements are positive, so they can be considered distances. The problem is, this is a velocity graph. It tells us their displacements. It never mentions that they started out at the same place. It appears as if they started out with a velocity of 0 We don't know if they started out from the same place or not. We don't know if they're going in the same direction. So we'd have to be given more information in order to be able to say something like this. Right now, all we can honestly do and confidently do is comment on the displacements, and that's going to be the difference in their displacements from a time of 0 to a time of 5. If we are given some information about them going in the same direction and starting at the same point, well, then something like this would definitely be an acceptable answer. In this case, we weren't. Now, let's look back at some things here before we get to slide 4. Everything we've done so far, we have had integrals in terms of the variable x. Whenever we have a y equals some equation involving x, y equals some equation involving x. When it's y equals equations, everything is going to be in terms of x as we set up our integrals. Same thing happened here. We had a y equals equation. We had a y equals equation. As we set up the integral, lower limit, the upper limit, integrand, everything was in terms of x. However, when we get to slide 4, well, now we're going to have some functions. Well, let's not even call them functions. Let's call them relationships, where they are x equals some function as a function of y. X is equal to some function as a function of y. And so here we've got, and again, I'm using that term function kind of loosely. This is not a function. It doesn't pass the vertical line test. But we do have a relation here, this green guy, which is an x equals. And then we got this red relationship here. And this is not one function above the other one. This is a function, again, a relation to the right of another relation. And things on the number line on the right are larger. This would be considered the large relationship, and this would be considered the smaller because it's located to the left. And so I'm going to use the word slicing. We're going to slice from large to small. And when we slice from the large one to the small one, we would have to have horizontal slices here. And so the integral is still going to be large minus small from a lower limit to an upper limit. But when you've got to slice horizontally to get from large to small, everything is going to be in terms of the variable y. So our area could be expressed as an integral in terms of the variable y when we have to slice horizontally to get from large to small. So let's take a look at an example here. We're going to find the area enclosed by, well, now, okay, that's a y equals. I would think that this would be something in terms of x. This is a y squared equals. Let's see what these guys look like. Now, y equals x minus 1. Y equals x minus 1 is an equation of a line. It's got a y-intercept of -1. It's got a slope of 1. . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . 1 . It looks something like that. Now this guy over here, this is an x equals y squared kind of a thing. And that's going to be a side opening parabola. So let's see what we've got here. Let's put in, let's see, what would be a nice number to put in for x. If I put in -3. If I put in x is -3, y is going to be 0. What if I put in x is, let's see, what's going to be a nice perfect square? X is, let's see, -2.5. X is -2.5. We have -5 plus 6, that's 1. So if x is -2.5, y could be either +1 or -1. Now, when we draw this parabola, we're going to draw this parabola, and it's going to go like this. But let's take a look at where these intersection points are. Let's find those x and y values, and that's going to happen. Let's see. If I were to solve this for x, I'd say I'd have y squared minus 6. That's equal to 2x. And so then I think I divide by 2. And that's what x would be equal to. So I think I'm going to divide by 2 by erasing this 2. And over here, solving for x is pretty easy. I've got x equals, and that would be y plus 1. And where do those things intersect? Well, that's a good question. Where does y plus 1 equal y squared minus 6 over 2? Well, let's see. Now, one thing that I've done here, and keep in mind, we do have x equals equations. And if we've got x equals equations, most likely this is something that is going to be in terms of y. So we're going to keep an eye on that. But let's work on solving this guy. I think I'd multiply by 2. I think I'd get everything over on one side. And so I'm going to say 0 is equal to, I've got a y squared here. Let's subtract 2y from each side. And let's subtract 2 from each side. Because I'm pretty good at figuring out when functions are equal to 0. So I think 0 is equal to, let's see, y minus 4 and y plus 2. So I think when y equals 4, these things are going to intersect. Or when y equals -2, these things are going to intersect. So down here, yeah, this looks like this could be y is -2. This looks up here as if it's possible that y is indeed 4. If I want to figure out what x is, I think this would be the easiest one to put those y values into. If y is 4, I think x is 5. If y is -2, I think x is -1. And when I try to slice this thing, if I thought, I'm going to try to slice vertically, because if I slice vertically, then everything's in terms of x's. My slice would eventually hit the x-axis. And so therefore, everything's in terms of x's. It's another way to remember it. If the big function is above the little function, and you slice vertically, whichever axis you hit with your slice, that's the variable you're going to use. And sure enough, blue is bigger than red, blue is bigger than red, blue is bigger than red. This is looking really good. Until I get over here. Now I hit blue as big, blue as little, and red isn't even involved in this region. And if that's the case, I can't slice vertically. I'm going to slice horizontally to get from big to little. I think red is on the right of blue for this entire region. If I slice horizontally, now my slice would eventually hit the y-axis, so I'm suspicious everything's in terms of y. Slice from big to little, and yes, my slices always start at red, always end at blue for the entire region. And these slices, being horizontal, would hit the y-axis. Therefore, the variable I'm going to use is indeed y. So the area between these functions is the integral. Now, big function is red, and red was the line. That was y plus 1. Minus the smaller function, which is located to the left. Y squared minus 6 over 2. I would need a dy to write this appropriately. What are my lower and upper limits? Well, those have to be y values as well. And the y started out at a low value of -2 and ended at a high value of 4. If I put this into my calculator correctly, well, why don't you put it into your calculator correctly? Press pause, come on back when you got an answer, and hopefully your answer is 18. So that's how we're going to find areas between curves, and it's important to know in which direction are we slicing? Vertically, in which case our slices would hit the x-axis as we go from big to little. Well, then everything's in terms of x. Or do we have to slice horizontally to get from big to little for the entire region? If that's the case, our slices would hit the y-axis. We need everything in terms of y by creating these x equals equations. All right, check out Schoology. There will be some practice in there for tonight.